Hello, good afternoon, and welcome to Hydromantis webinar. Today we are going to talk about modeling of anaerobic digestion processes in GPSX. My name is Rajiv Goel, and I have my colleague Spencer Snarling here with me, so we'll be taking care of this webinar today. Just to walk you through the agenda here, we are going to talk about a little bit about the introduction of anaerobic digestion models, going with some of the biological models that have been implemented in GPSX. Also, we'll look at an application example, and we'll let you know some of the upcoming events that are planned for the next month at Hydromantis, and we'll follow up with some of the questions from you. So first of all, anaerobic digestion process, as all of you know, is one of the key important solid processing process in wastewater treatment plants. The main purpose of anaerobic digestion process is to do solid reduction and also to achieve solid stabilization. In recent years, there has been a lot of emphasis on energy recovery as well, and anaerobic digestion is gaining more and more importance with respect to energy recovery options. Also, since there are a lot of new regulations with respect to discharge of nutrients in the effluent, the side streams which are rich from the solid processing facilities, which are rich in nutrients like nitrogen and phosphorus, the recycling of those nutrients back to the liquid train is also an important consideration. Also, anaerobic digestion, especially like the fermentation aspect of anaerobic digestion, is sometimes becoming an important feature at wastewater treatment plants, in which some extra fermented substrate is required for BioP removal. Now, just before going into the biological models for anaerobic digestion that are available in GPSX, we are going to just to talk about some of the philosophies that are used to develop anaerobic digestion, or to couple the liquid train models with the anaerobic digestion models. So there are two approaches that we normally see when we are trying to look at anaerobic digestion models. So in the first approach, we have the models for example, the activated sludge tanks, or the liquid train models, in which we are mostly modeling heterotrophic bacteria, nitrifiers, and some of the substrate like slowly degradable substrates, readily degradable substrates. So there are some states which are modeled in the liquid train, and they are done through a kind of a well-defined model like activated sludge models. Then when we come to anaerobic digestion, some of the species which are normally there in a liquid train system, they are not the one doing the job in anaerobic digestion, and there are some specific bacteria which are working in anaerobic digestion stage. So, and some of the states, basically with respect to substrate itself, are very different than the states which are used in liquid train models. So in one of the in the early approaches in which the liquid train models and the anaerobic digestion models have been developed in isolation, the approach has been to combine this model 1 and model 2, or use this model 1 and model 2 through a state variable mapping. So all the states which are coming out from liquid train models, they are somehow mapped into the states which are used for anaerobic digestion. And when we recycle some of the stuff from the effluent of anaerobic digestion back to the plant, then we do need some kind of inverse mapping for the states. So in this particular situation, what's happening is that all the states which exist in anaerobic digestion, they get lost when they come back to the mainstream here in the liquid train. So this is kind of a concept which was kind of used when activated sludge models were well developed, but anaerobic digestion models were kind of developed in a little bit of isolation. Another concept which we can use to model anaerobic digestion processes is just by defining a very comprehensive model, which includes all the states which are for example, which includes all the biological biomass species which are active in the liquid train as well as in anaerobic digestion stage. So in this particular model, we are tracking all the states throughout the plant, and the processes which are defined underneath, they become active depending on the electron acceptor conditions in different part of the plant. But all the reactions are there and they become active only when they need to be active. So for example, if there are anaerobic bacteria, then they will get active only in the anaerobic digestion stage, and they will do only a little bit of function or very little function in the liquid train. So in this particular approach, basically, all the states of the model are available throughout the plant, and this is also known as a kind of a super model type of approach for modeling the whole plant. Now coming to some of the digestion models that we have in GPSX, we have actually 4 models in GPSX that you have access to. The first and the basic first model that was defined for anaerobic digestion in GPSX is known as a basic model. It's a very simple model, and we'll get into the details of each one of them as we go along through this slideshow. The second model, which of course is coming out from the IWA task group, is known as anaerobic digestion model number 1, and it's a kind of a bit more complex model, and also considered kind of a detailed modeling of degradation. We have 2 other models which are implemented in GPSX. The one is MantisAD, and this is an attempt actually to simplify the model that has been proposed, or that is the model ADM. So it's a kind of a simplification of ADM1. It is developed in-house model, and it's as I said, it's an intermediate, has an intermediate complexity between basic and ADM1 model. MantisAD model is an in-house model. It's a very advanced model, and it's based on the philosophy, the second, the philosophy of the comprehensive modeling. So it's a kind of a super model kind of approach. So we are going to talk about a little bit on each model and see what are the differences and where to use each one of them. So first of all, the basic model, it comes from the work from Andrews in 1969, and with some modifications. And as you can see, the modifications are listed here on the right-hand side. There is a pH estimation algorithm, which has been included with this model. We have the temperature sensitivity. Also, to differentiate between organic and inorganic compounds, we have extra states which define the inert inorganic particulates. Also, one extra addition is the toxic substrate degradation and the toxicity effect on methanogenic bacteria. So in this particular scheme, if we look at the overall scheme of degradation, we can see that it's a 2-step process, and the initial starting material for this model is the composite material, which is classified as VSS. So VSS essentially is composed of all the biodegradable and non-biodegradable material, and it's hydrolyzed, and the acid production step is included in this particular step itself, producing short-chain fatty acids, which are then used by the methanogens and create and produce methane and carbon dioxide. Additional component which I talked about, there is a generic toxic compound that can be defined, and the toxicity of this compound on methanogen is included in the model. We look at what are the key points for this model. It's a very simple reaction scheme, but being simple also has its own downsides, because all of the organic states, for example, the inert organics and the biodegradable organics, are lumped into one single parameter VSS, and that makes it really kind of, from plant to plant, there might be a need to actually calibrate or change the value of the degradation constant if we are using just one lumped parameter without giving consideration to the relative fraction of biodegradable and inert substrate. Another consideration is that there are no phosphorus transformations built into the model. We have some simple mass balance with respect to phosphorus, but there is no elaborate phosphorus transformation that is built into this particular model. Also, the carbon balance, there are some carbon dioxide production happening while degradation of the solids and uptake of the acetic acid, but again, this is kind of a balance which is defined by the user, but it's not really a very rigorous carbon balance that takes place in the system. Again, if we look at the philosophy for this model development, in this particular case, it is an independent model, and it does require influent and affluent state variable to be transformed. So when we are connecting this model with the liquid train models, depending on what model we are using in the liquid train, we do need to have some specific influent and affluent state variable transformation interface. Now coming to our most advanced model, it's called Anaerobic Digestion Model, as proposed by Batstone et al. In 2002. As you can see that this is a much complex scheme than the simple model that I just described. The main differences are that there are several stages. So in the simple model, we had only one bacterial species, methanogens. Those are being modeled. In this particular case, we have 7 bacterial species that are working on different substrates. That's one thing. So there are 7 number of species, and the second important point is that the material coming into the digester has been characterized from the perspective of whether it is carbohydrate, proteins, or lipids. And each one of these compounds are then has their own degradation kinetics, and there are a number of intermediate compounds that are defined here in this particular model, including propionate, valeric acid, butyric acid, acetic acid, and hydrogen. So it's a very complex model. However, it has its own utilities when you have a kind of a well-defined influence with respect to all these components like carbohydrates, proteins, and lipids. And sometimes we know that in wastewater context, the sludge coming out from our secondary clarifiers or coming out from primary clarifiers, it's not so well defined with respect to these particular compounds. So, it's a pretty well defined scheme, a very complex model, and it has its own utilities. But with respect to wastewater component, there is still some downsides of using this. So the key points, it's a complex model, like I said. There are some issues with respect to robustness of these issues. It requires quite extensive setup, and it requires quite extensive time to set it up. One of the key weakness of the model is that there is no phosphorus transformation. So if you're working with a BioP system, or if you're working, for example, if you're interested in how much is the phosphorus recycling going on, it's just based on the mass balance, but there are no kind of specific phosphorus transformations that are going into the system. Also, the model does not have precipitation reactions, and as we know, sometimes we are interested in seeing whether there is right precipitation happening in the system, or there are some other precipitates that are forming in the digester. So those reactions are missing from ADM1. Again, this is based on the philosophy of first type of philosophy, in which the two models, the liquid train models and the solid train models, are different. So there is an interface requirement, and since the structure of ADM1 is very complex, the state variable transformation interface are very complex in nature for this particular model. Now coming to the third model, which is MantisAD, and the motivation for this particular model has been to have a simplification over ADM1 and to provide a kind of a sound, robust model which can, with some simplification, which is valid, which is still valid for wastewater treatment applications. So in this particular case, the material, the composite material, which is basically the biomass, the particulate inerts, slowly biodegradable material, all those materials are classified into two different categories. One is a rapidly biodegradable material, another one is a slowly biodegradable particulate material. And this material gets disintegrated and converted into these two class of materials here, and each one of them then gets hydrolyzed and acidified and get converted into slowly biodegradable soluble material and rapidly biodegradable soluble material. And both of these materials then go through the phase of acetogenesis, producing acetate and hydrogen, and ultimately leading to methane formation. So this is a relatively simpler scheme than ADM1, but of course we are sacrificing some of the details that are there in ADM1, but it does still work pretty well if the objectives are with respect to VSS degradation, gas production, and those kind of, and we are not particularly paying too much attention to the kind of the details of the intermediates that are being formed during the anaerobic digestion process. So if we look at some of the key points for this one, the focus is mainly wastewater treatment plants. The anaerobic digestion in the wastewater treatment plants is based on ADM1 but much simpler, and it can be easily interfaced with common activated sludge models. Also, one of the benefit of using this one is that it's kind of mechanistic, but still it can be easily calibrated using commonly measured wastewater treatment digester performance indicators. Now coming to our whole plant model, which is built around the philosophy of a comprehensive modeling in which all the states flow around the whole wastewater treatment system. This model we are calling MantisAD Model, and it's the anaerobic digestion part of this model is built around the modifications of University of Cape Town Anaerobic Digestion Model number 1. So what we have done in this particular process is that our starting point starts with some of the key state variables that are being used in the liquid train. For example, when we are passing the sludge from the primaries or the secondaries, the main component of those sludge is heterotrophic biomass, nitrified biomass, POWs, inert decay products, and the inert materials, also slowly biodegradable substrates. So these are the starting points that are being fed to the digester. And inside the digester, the assumption or the processes by which all these are getting degraded is through the process of the biomass, which cannot grow in the system, is assumed to decay. So all the heterotrophic biomass, nitrifiers, and POWs, since they cannot really grow in anaerobic digestion stage, so they are anaerobically getting decayed and producing some of the slowly biodegradable material and the fermentable COD. And the slowly biodegradable material that comes into the anaerobic digestion gets hydrolyzed. So essentially our starting point in MantisAD for anaerobic digestion is all the key states that are available or that are basically monitored in the liquid train. So it keeps a very consistent structure and helps us track each and every state throughout the plant. So the scheme of degradation after the fermentable COD is to have basically the fermentation from the fermentable COD and produce basically acetate, hydrogen, and propionate. So those are the three key intermediates that are being considered in this model. We are not considering the higher long chain like valeric acids, butyric acid, or some of the other intermediates that are being used in ADM1. So we kind of just have only the three intermediates that are, we think those are the most important ones in the context of wastewater treatment plants. So again, here we have 4 different types of biomass. We have fermentative heterotrophs. We have acetogenic biomass, which actually produce acetate from the higher order VFAs. And also we have acetoclastic methanogens, which are producing methane using acetate. And we have hydrogenotrophic methanogenesis, in which we are using hydrogen and CO2 to produce methane. So it's a kind of a reasonable level of details that are needed to model anaerobic digestion, and it does account for all the kind of effect of, for example, the hydrogen in the system, and it does have some kind of inhibition feedback mechanism to produce propionate or acetate in the system. So the key point for this is it's a complex model. It has reasonable amount of complexity, but just because it's a supermodel, it has a complex structure. So it's much more complex than any other model that we have, but it has been optimized for robustness. So when you use this model, you will see that it's much more robust than ADM1 model. Also, we talked about different balances in ADM1, and the MantisAD model actually uses the elemental balance for carbon, nitrogen, phosphorus, oxygen, calcium, magnesium, and potassium. And as we know that more and more needs are, as we go forward, there are more and more needs for keeping track of more and more compounds in the total overall mass balance of the waste at different stages of the wastewater treatment plant. So, for example, if we are interested in struvite precipitation, we also want to keep track of magnesium, and MantisAD actually provides you the flexibility to do that. Also, we have several precipitation reactions, the most important ones included in MantisAD, and as I said before, it's a whole plant model, and therefore we don't have to go through complex interfacing between liquid train models and the solid stream models. So it's a kind of a whole plant model, it's kind of a super model which tracks each and every state of the plant throughout the wastewater treatment plant. Now, if we compare the structural complexity, we can see that basic model only has 6 number of processes, number of state variables are 8, number of biomass only 1, so we are only tracking methanogens here. MantisAD, number of processes is 13, number of state variables 22, number of biomass population 4. ADM1 we have 19 number of processes, number of state variables 24, and number of biomass population 7. MantisAD, which is the most advanced one, and this is not specifically related to anaerobic digestion, all this information which is done here, but it is, as I said, it's a supermodel and includes kind of all the other details which are available in liquid train models as well. So now, one question that normally is asked is what kind of inhibitions that we are modeling in different models. And in the basic model, we are modeling we are having a generic toxic compound which can inhibit the methanogen activity. In the MantisAD and ADM1, we are tracking the pH, hydrogen, and free ammonia inhibitions on different bacterial species here. For MantisAD, we have pH and hydrogen. We don't have the free ammonia inhibition of the methanogens at this stage for MantisAD. Another thing, after looking at all the 4 models, the question arises, okay, which one should I use? Our recommendation normally is to, if you have the simpler modeling needs, then probably MantisAD is the best choice. It gives you a reasonable estimation for the gas production and VSS destruction rates. If you want to do more complex modeling, then we normally would like to recommend MantisAD. It does the elemental modeling, has a detailed ionic speciation model, and the precipitation reactions. In situations where you have detailed influent characterization with respect to what are your proteins, what are your carbohydrates and lipids, and for co-digestion type of applications, probably ADM1 is kind of probably a better choice. We're running a little late here, so just to go through some of the anaerobic unit processes that we have. We have 3 unit processes available to you, which you can use to model anaerobic digestion processes in GPSX. The first unit process, anaerobic digester. So this is a typical unit process that is used in the solid processing system. We have USB and EGSB reactors and the anaerobic MBR, and both of them find its utilities in high-strength wastewater, especially soluble in nature. And one of the main feature of EGSB reactor is that we do have bed fluidization model. So what you can do is you can try to track the bed height in EGSB reactors. Anaerobic digestion model is different from this anaerobic digestion model with respect to having a solid liquid separation component built into this particular reactor. Now I wanted to give you just a quick example layout which we prepared in Mantis 2, and this is a very, very simple treatment plant in which we have an influent, a batch influent. All the flow, basically there is a bypass functionality which is not being utilized. All the flow is going to aeration tank, then to clarifier. From clarifier we are withdrawing sludge, we are wasting sludge, which is fed to a thickener. The thickened sludge goes to the digester, and the digested sludge is taken and for disposal. So this is a kind of a very simple layout, and I would like to just show you some of the important features of this layout. So this is a layout which we prepared in GPSX 6.4. This is the same layout which I described, and to show you what we mean by the super model or the tracking of all the states, if we look at our influent characterization here, we can see that we do have in the influent the facility to actually specify the acetogenic biomass, acetoclastic methanogen, hydrogenotrophic methanogens. So these are the state variables which are being actually, these are part of the influent, and these are being tracked throughout the model. So we have all the anaerobic states, all the anaerobic biomass species, all the elements or the kind of inorganic compounds which like calcium, magnesium, potassium that might be flowing through the system. So all this can be specified in the influent, and once they are specified, their fate in the system is determined, and it flows in the liquid train and then ultimately finds its way into anaerobic digester. So if we look at the anaerobic digester specification here, what we need here is we need to just specify the volume of the digester. And in 6.4 we have added another factor, which is the effective volume fraction. Sometimes we have seen that sometimes the full volume of the digester, due to the mixing or maybe accumulation of some inorganic material, all of the volume is not effective. So we have added another factor, which is the effective volume fraction, by default a value of 1, but depending on the data which you have, you might want to change this one. Also, another one parameter is the KLA, which is a kind of mass transfer rate coefficient due to mixing, which needs to be specified. So these are some of the parameters that you need to specify for anaerobic digestion. Also, when we talk about, for example, the kinetics here, you can see that all the kinetic parameters which are related to anaerobic digestion are available through the kinetic parameter menu here. So fermentative biomass, acetogenic biomass, hydrogenotrophic methanogenic biomass, acetoclastic methane. So all the parameters that are kind of required for modeling anaerobic digestion process, you have access to all of those through the digester kinetic menu there. So this is a very simple exercise which we have set up here, and we have already run the model here. So when we look at the digester properties here, we can see that the HRT 30 days, effective HRT 30 days, there is a total gas production, which is 80.4 meter cube per day for this one. VSS destruction 45.1. So it does keep track of all the important parameters. And if we look at the profiles, or just kind of a very small run, dynamic run, which we have done here, it shows you the amount of biogas that is being produced, how much is the fraction of the methane in the total biogas. Also gives you the information about pH and alkalinity in the system. VSS removal efficiency, which is being tracked here, 45%, and also with respect to the nitrogen and phosphorus, so we can track what are the ammonia values and the phosphorus values coming out in the effluent here. One good thing about this kind of integrated modeling is that you can evaluate the effect of upstream changes in the upstream parameter values on the digester performance. For example, if we want to change the SRT of the system in the upstream of the system, how does it affect my digester gas production? If I change my influent and change the influent inert organics that are being fed into the system, how is that going to change my digester performance? Also, just within this system itself, of course, we can evaluate the effect of the kinetic parameters, but also with respect to the mass transfer rate for the CO2 and the methane. So we have done. So coming back to our slideshow here, we have done some analysis for just to show you that how do you evaluate the effect of SRT in bioreactor. So we are talking about now a change in the upstream here when we are changing the value of the SRT from a value of 6 days to a value of 16 days here. We can see very clearly how that change is going to affect my gas production in the system. So we can see that as we are increasing the SRT and mineralizing more and more solids in our aerobic system, our biogas production potential goes down from anaerobic digestion. Also, it does have effect on the solid VSS removal efficiency because more inerts are being fed into the digester. So we can see that our efficiency, solid removal efficiency also goes down. Also, it has effect on how much ammonia and how much phosphorus are going to come out from anaerobic digestion, and also the effect on the pH and the alkalinity. When we change the influent fraction, for example, inert organic fraction, so for example, keeping the COD value to the same number, but we are changing the fraction of the inert organics that are being fed into the system, and we can see how that affects the performance of anaerobic digestion. So in this particular case, we are doing evaluation with respect to when the influent fraction, inert organic fraction in the influent ranges from 0.1 to 0.2, how is that going to change the gas production in the system? We see gas productions are reduced as the inert material is increased, VSS degradation efficiencies are reduced, and it does have implications on pH, alkalinity, and nutrients that are being discharged from the effluent of the anaerobic digester. Also, the mass transfer rate, this is an extreme case, but what happens if our mixing is not really good in the digesters and there is a limitation of separation of the CO2 and the methane gas. So as we would like to expect, if the mixing is not really good, then in that case more CO2 remains soluble in the system, more CH4 remains soluble in the liquid, and it gets out from the anaerobic digester. And that's why we can see that if our mixing is not great, our biogas production, well, biogas production is probably the same, but what comes out in the gas phase reduces, and as we increase the mixing, it comes to kind of more and more gets stripped out. Also, when there is a more CO2 trapped in the liquid, we can see that our pH is kind of on a lower range, and when we strip that CO2 out, then more and more the pH tend to increase. So these are some of the kind of studies that you could take, and this is not the intention to kind of show each and every case here, but just to give you an idea what you can do with these models. Also, one of the main questions that normally is asked, what are the typical calibration parameters that I need to adjust? So when we're talking about an integrated model or a comprehensive model, then the main important thing is that we need to have a good influent characterization. We need to, because the relative ratio of inert organics and biodegradable organics can directly affect how much, can directly affect the downstream solid processing or the anaerobic digestion process. So it is one of the important thing to look at. Also, since we are feeding waste activated sludge, which is rich in heterotrophic biomass, the anaerobic decay rate of that heterotrophic biomass can play an important role. Also, the hydrolysis rate, because those are the starting points and those are the rate limiting steps in anaerobic digestion. So these are some of the things you might want to change to increase the flux of substrate to the methanogenesis stage. Also, the fermentation rate can sometimes vary and sometimes can change. So that is something which we modify sometimes. Also, one consideration is if you are looking at the relative proportion of methane gas coming out from the digester, then sometimes the substrate carbon to COD ratio can play an important role too. And you have the option to actually change that in the influent characterization. So that is sometimes maybe helpful to address the issue of not having the right proportion or the fraction of methane gas in the biogas that is produced from the anaerobic digester.